Hello students, here's another video lesson. This is Unit 9, Lesson 2. We're going to be talking about polygon rotation. In the first lesson, we talked about what a polygon is. Here, we're going to be talking about what happens when we spin these bad boys around. The target is I can analyze rotations of 2D shapes around either their center, that's depicted here in the green spot here, or their side, and that's depicted in both of these pictures, and predict the results of these rotations. Here we go. For the do now, what you had to do is take a look at the sample question here. It was from a past exam, but most students chose B, which is the wrong answer. So pause the video, check out these 4 questions, and try to figure out what went wrong here. Okay, most students chose B because they weren't sure what the question was really asking. It's asking for the rotational symmetry of an equilateral triangle. We'll get to that in a second. They might have seen the words equilateral triangle and circled the number of degrees in an interior angle of that type of triangle. You can see an equilateral triangle here. Each of these angles is going to be 60 degrees because 180 degrees inside of a triangle. If I'm dividing that evenly by 3, 180 divided by 3 is 60. The correct answer to this question is 120 because of the formula that we learned about a few units ago. This is the rotational symmetry formula. We learned about it with transformations. It's 360 divided by the number of sides of the shape. That's equal to 120. It turns out that if you rotate a shape, a triangle, around itself 120 degrees, the computer is not spinning it correctly, but you can see it completely overlaps that triangle. And if I spin it another 120 degrees, that's 240 degrees. Again, it's completely overlapping its original image, its pre-image. If you spin it another 120 degrees, voila, it is covering the triangle. However, we don't say that 360 is part of its rotational symmetry because if you spin anything around 360 degrees, it lies on itself or it maps onto itself. So we don't ever say that 360 is a measure of rotational symmetry for a shape. So for the section D, what other angles of rotation? We have 120 here, and then we add it to itself or multiply it by 2 to get 240. The situation is we add it to itself until we get to 360, and then we cross off the 360. You should remember this from the transformations unit. Remember the rotation formula looks like this. It's the angle of rotation equals 360 divided by n, which is the number of sides. In this example, this is a hexagon, a 6-sided shape, and each of the angles of rotation are 60 degrees. In other words, 360 divided by 6 is equal to 60 degrees. If I rotated another 60 degrees, it'll still overlap itself. Another 60 degrees, it'll still overlap itself. That's where all of these angles come from. 60, 120, 180, and so on. All of these are just 60 plus 60 plus 60 plus 60 plus 60. And again, we cross off 360 because we don't use that. For the check for understanding, state all the angles of rotation that will allow this regular pentagon to carry onto itself. Remember how many sides a pentagon has. Pause the video, try this out using the formula from above, and then see if you get it right. All right, hopefully you got 72, 144, 216, 288, and 360, right? You cross off that 360 because every time we're finding angles of rotation, we do not include 360 degrees. Moving on to the next page, this is an exploration. Instead of rotating a shape around its center, instead of spinning this shape around to the right or around to the left, what if we were to rotate it about one of its sides? So what I want you to do right now at your desk is take a piece of paper or any other sort of rectangle that you have lying around, maybe even your phone, and try to spin it around one of its sides. Not around the center, not horizontally, but like a vertical spin. Hold your phone vertically towards you and then try to spin it on one of its sides. What kind of shape would that make? Pause the video, try that out, and then come back to see what we say. All right, in order to motivate this discussion, I wanted to show you a picture from real life. This is a picture of a revolving door, and here's another picture of a revolving door. You've seen these before. They install them in buildings to prevent heat from escaping or coming in, as the case may be. It's to regulate temperature in the building. But anyway, you can see that this shape, this rectangle, has a central axis here. And you can see that each of these 4 rectangles have a central axis here. In other words, this rectangle is going to be spun on its side, on its right side here. And this rectangle is going to be spun by a line that's drawn directly through here. Here's a picture example. This line is drawn directly in the middle of this rectangle, so you can see the rectangle spinning. And this rectangle has a line drawn on one of its sides, and it's spinning around it. As it spins more and more frequently, as it revolves, it doesn't form a 2D shape anymore. It forms a 3-dimensional shape. That 3-dimensional shape is suggested by the housing of the door. You can see this door has this round ring here and a round ring on the bottom here, another round ring here and a round ring on the bottom. This is a cylinder. A cylinder is a 3-dimensional shape with round faces on the top and bottom and a rectangular curved base here, or a rectangular curved side, I should say. So moving back to the question here, instead of rotating a shape around its center, what if it were rotated around one of its sides? It would form a cylinder, and it looks like this. All right, you can see if I took this rectangle and spun it around this side here, this right-hand side, it would spin around in a circle like this, and it is creating that cylinder shape. In each of these examples, it's asking what if the rectangle is continuously rotated, and what if the right triangle is rotated around this leg. Pause the video and try to draw this out. Sketch it out the same way that we sketched out this rotation, and then come back to see if you got it right. All right, you can see that this rectangle, I spun it around side W or about side W. Sometimes they use that phraseology there. I drew the axis here, and then I drew it circling around. It kind of looks like a hockey puck. It's a cylinder still, but it's a very short, very wide cylinder, whereas this one, we spun it around one of its long sides, and it makes a slightly narrower, slightly taller cylinder. For the right triangle, it does rotate around in a different way. It's rotating around RS, which means R isn't really going anywhere, but T is going all the way around this axis. So T is making that circular motion there, which means it's the base of this cone, and the top of the cone doesn't really move anywhere because it's on that axis of rotation. So we can identify these shapes, these 3D shapes, which we're going to be calling solids, by writing them in here. In fact, what we did here was we wrote in the rotation will form a cylinder, a cone, and this one a cylinder. You should be able to also speak to what the characteristics of the cylinder are. You can tell that this cylinder, for example, is taller and thinner than this cylinder here. All right, moving on to the check for understanding. What object is formed when these things are spun in those ways? It does not give you pictures, so you have to draw the pictures and then describe what's going on. So pause the video, try that out, and then see if you got it right. All right, for this first check for understanding question, it did form a cylinder with height of BC. I was very specific about this one because we were able to say BC was the height of that cylinder. We can also say that the radius of the base of that cylinder is AB and CD respectively. We're going to get more into measuring 3-dimensional shapes or solids a little bit later in a different unit, but I wanted you to be introduced to the idea that a cylinder is going to have a height, and it's also going to have the radius of one of its bases. And in section B, which object is formed, this is a cone. We can tell that it's asking us to rotate the equilateral triangle MET about its altitude, and altitude is a perpendicular line that passes through a vertex. So we drew an altitude, and then we rotated that shape around the altitude. You should be able to take any 2-dimensional shape, draw a line through it, or use one of its pre-existing lines, and rotate it around. The most popular questions that they will ask are about cylinders and cones, or about rectangles and triangles, respectively. You must know that when you rotate these shapes around, you will form these types of solids. All right, that was the mini lesson for Unit 9, Lesson 2 on polygon rotations. Hopefully we hit this target. The target was I can analyze rotations of 2D shapes, which we did, and then predict the results of these rotations. We predicted these results, and here's a little callback to the beginning of the lesson where you saw this cone and you saw this cylinder, and you were saying to yourself, I wonder when we're going to learn about these. But I don't want to leave you without a joke like I did last time, so here's the joke. How much do you pay for dead batteries? Well, they're free of charge. All right, students, good luck studying.